The last topic in the Physics 3 unit is atomic and nuclear physics. In this lecture we're going to revise our ideas about basic atomic structure, and then we're going to define the three most common types of radioactive decay. Atoms consist of negatively charged electrons surrounding a very small positively charged atomic nucleus. The electrons are bound to the nucleus by electrostatic attraction between the negatively charged electrons and the positively charged protons found in the nucleus. So in the most simple atom, the hydrogen atom, we have a single electron electrostatically bound to the single proton that makes up the hydrogen nucleus. In the next most simple atom, the helium atom, we have two electrons electrostatically bound to the nucleus, which consists of two protons. So in this case we have to ask the question, if we've got two positively charged protons in the very small space of the nucleus, what is it that stops them flying apart due to electrostatic repulsion? And the answer is that the electrostatic repulsion is overcome by a stronger force known as the strong nuclear force. The strong nuclear force is greater than the electrostatic force, but it only operates at very short ranges, so at distances of 10 to the minus 15 meters or less. And the strong nuclear force is the force that binds protons and neutrons together. So in the helium atom we have two protons, which means we have to have two neutrons, and the nucleus, consisting of these four particles, is bound together by the strong nuclear force. The diagram here represents the basic atomic structure. So we have the small nucleus containing protons and neutrons, which collectively we refer to as nucleons. Then this nucleus is surrounded by electrons. Sometimes we refer to it as an electron cloud. You can think of the electrons either as being in orbit around the electron in the Rutherford or Bohr model of the atom. Or in the Schrödinger model you imagine the electrons as standing waves. But either way, this electron cloud has dimensions measured in angstroms, whereas the nucleus has dimensions measured in femtometers, where there are 100,000 femtometers to 1 angstrom. So the nucleus really is a very, very small volume in comparison to the overall size of the atom. Just reminding ourselves of some definitions referring to atomic structure. The number of protons is called the atomic number, denoted capital Z. The number of neutrons is the neutron number, denoted by capital N. The mass number of a particular atom, capital A, is simply the total number of nucleons. So the neutron number plus the atomic number. This slide illustrates the standard notation used in nuclear physics. So we're using the example of helium, and what's represented here is helium-4. The atomic number Z for helium is 2. So this is shown as the subscript. It's the atomic number, the number of protons, that defines the element. The atomic number is unique to a particular element. So helium always has 2 protons. So if the atomic number is 2, we know we're dealing with the element helium. The superscript 4 refers to the mass number. And the mass number, as we've just seen, is the total number of nucleons, in other words, the number of protons plus the number of neutrons. So in this example, helium-4, we know we must have 2 neutrons because the atomic number 2 tells us that we've got 2 protons, mass number of 4, so the number of neutrons is just the mass number minus the atomic number. Continuing with the notation and terminology, it's worth pointing out that in nuclear physics we tend to refer to atomic nuclei as nuclides. This reflects the fact that in nuclear physics it really is the nucleus that we're interested in. We don't take into account the electrons, though these are important obviously for determining the chemical properties of an element. In nuclear physics it's the nucleus that we're interested in. The next point to note is that we can have elements which have the same atomic number, because remember the atomic number defines the element, but different numbers of neutrons. Where we have nuclides which have the same atomic number but a different number of neutrons, we refer to these as isotopes of the element. So for example, gold, which has an atomic number of 79, in other words 79 protons, has 30 different isotopes ranging from gold 173 to gold 204. Interestingly, only one of them, gold 197, is stable. The remaining 31 are unstable nuclides or radioactive nuclides. Atoms which have unstable nuclei we refer to as radioactive. So radioactive atoms or radionuclides are ones which can spontaneously change from one form to another or from one state to another by the emission of particles. This is what we refer to as radioactive decay. And there are 3 major types of radioactive decay. We can classify it into 3 common types: alpha, beta and gamma. In gamma decay, the nucleus does not change to a different element. So the atomic number, the number of protons, is unchanged in gamma decay. However, in the other 2, alpha decay and beta decay, the element does change. The nuclide changes its atomic number, the number of protons changes, so the element changes from one element to a different element. We're going to start by looking at gamma decay. in an atomic nucleus, the nucleons have certain allowed energy levels. So this is just like the electrons in Bohr's atomic model. There are certain energy levels that the nucleons can have, and they can transition from a higher level to a lower level by emitting a photon, and the photon would have an energy equal to the difference in energy between the two levels. Because the strong nuclear force is much greater, much stronger than the electrostatic force, the difference between these energy levels is also much greater. So the photon that's emitted, what we call the gamma particle, is very high energy. So gamma radiation is made up of gamma particles which are just high energy photons. We know that gamma radiation is simply a form of electromagnetic radiation. The photons will have energies in the range of 100 kiloelectron volts or more. So gamma decay doesn't involve a change in the atomic number, so the element doesn't change. It's simply the nucleus changing from one energy state to another, but the element remains the same. Gamma radiation is ionizing, but the ionizing power is relatively small. However, the gamma particles, being photons, are very small, have significant energy, so they have a high penetrating power. They can pass through most material and will only be stopped by a significant thickness of a dense material such as lead. So alpha decay occurs by the emission of an alpha particle. An alpha particle is simply a helium-4 nucleus, in other words 2 protons and 2 neutrons. So in alpha decay, when the alpha particle is emitted, the mass number goes down by 4, the 2 protons and the 2 neutrons, and the atomic number goes down by 2. So the element does change. Alpha decay tends to occur in nuclides which have a large mass number. In other words, contain a large number of nucleons, because these large nuclei tend to be more unstable. And the reason for that is simply that we have two opposing forces working against each other in an atomic nucleus. We have the electrostatic force, which is tending to push protons apart due to electrostatic repulsion, and we have the strong nuclear force, which is tending to bind the nucleus together due to the attraction between the protons and the neutrons. However, the strong nuclear force is a very short-range force, and it drops off rapidly as distances increase. So in a large nucleus, where the average separation between nucleons gets bigger, the strong nuclear force is more in balance with the electrostatic force. That's why these large nuclei tend to be unstable. And in such a large unstable nucleus, the alpha particle can escape because it's less tightly bound. Alpha radiation is highly ionizing. Obviously the alpha particle is, relatively speaking, a massive particle, 2 protons, 2 neutrons. It's emitted at high speed, so the energy of an alpha particle typically is in the range of 5 to 10 mega electron volts. So it's highly ionizing. However, alpha radiation has a relatively low penetrating power because it's such a large particle. So it's stopped within a few centimeters of air, or it's stopped by a sheet of paper. It's certainly stopped by skin. So although it's highly ionizing, it's not so dangerous unless, of course, it gets inside the body. If you ingest something that's an alpha emitter, it will cause damage. It's highly ionizing, but with a relatively low penetrating power. Beta decay occurs through the emission of a beta particle. There are two types of beta particle. There's the beta minus, which is simply a high-speed electron, or the beta plus, which is a positron. In beta decay, the mass number, the total number of nucleons, is unchanged. So A stays the same. Because beta decay involves either a neutron turning into a proton or a proton turning into a neutron, but in either case the total number of nucleons doesn't change. Beta minus decay occurs when we tend to have relatively larger number of neutrons compared to protons. Beta minus decay is when a neutron changes into a proton, so the atomic number goes up by 1. If we're creating a proton, a positively charged particle, we also have to create a negatively charged particle in order to conserve charge. Charge has to be conserved in the decay, so if we create a proton, we have to create something with an equal and opposite charge. In this case, a beta minus decay, that's an electron. And it's that electron, which is the beta particle, which is emitted. In beta plus decay, well, this tends to occur if the ratio of neutrons to protons is smaller, so we have relatively fewer neutrons compared to the protons. And beta plus decay is a proton changing into a neutron, so the atomic number goes down by 1. And again, in order to conserve charge, because we've lost a proton, we have to create a positively charged particle, and that's the positron or the beta plus particle. The beta particle that's emitted, so the electron or the positron, tends to have an energy in the range of roughly a half MeV. So it has a medium ionizing power. It also, due to its size and the speed at which it's travelling, tends to have a medium penetrating power, so it will be stopped by a thin metal plate. So it has more penetrating power than alpha particle, but less than a gamma particle. So on this last slide we have a plot of the known nuclides. So all the different isotopes of all the elements are plotted. On the vertical axis we have the atomic number, the proton number, and on the horizontal axis the neutron number. And if you look at the data points, the green data points represent stable nuclei. The gold ones are the radioactive or unstable nuclei. And it's interesting to look at the curve. The red line on the graph shows n equals z, in other words, where we have the same number of neutrons as protons. And if we look at the low atomic numbers, so for example anything below calcium, which has an atomic number of 20, we can see that the stable nuclei lie on that red line, because the most stable configuration of the nucleus is when we have the same number of neutrons as protons. But as we go up to higher atomic numbers, to larger nuclei, we see that the stable nuclei tend to lie below that red line. And the reason for this is, as we mentioned on a previous slide, that as the nucleus gets bigger, the influence of the electrostatic force tends to grow in comparison to the influence of the strong nuclear force. So the repulsion between protons is relatively larger, and the way to keep the nucleus stable is to counteract that by having more neutrons, which obviously are neutral, so don't contribute to the electrostatic repulsion, but do increase the binding due to the strong nuclear force. So as we go up to higher atomic numbers, we can see that the stable nuclei lie below the red line. But then on either side of that green line, we see that we tend to have the unstable isotopes. And again, that happens because we get an imbalance between the number of neutrons and protons, which tends to lead to beta decay, as we saw on the previous slide. So the larger nuclei are prone to radioactive decay, either through alpha decay or through beta decay.